My name is Spatial. I'm the director of TISED, and it's really wonderful to see such a great turnout. Before I start introducing our speaker today, I'd just like to, on behalf of TISED, acknowledge that McGill University is located on land which has long served as a site of meeting and exchange among indigenous people, and a territory on which we are fortunate to gather today. So with that, it's a real pleasure to introduce my colleague, Professor Sarah Jordaan. Professor Jordaan is an associate professor with joint appointment at TISED and in the Department of Civil Engineering. Professor Jordaan joined in September, early September, and so it's a real pleasure to have her as part of TISED. And before Professor Jordaan arrived here, she was an assistant professor at the Johns Hopkins University with the School of Advanced International Studies and the Department of Environmental Health and Engineering. That's right. Mm-hmm. And prior to that, she was assistant professor of energy policy and politics at University of Calgary with the Department of Political Science there. Professor Jordaan received a PhD in 2010 from the University of Calgary at the Institute for Sustainable Energy, Economy, and the Environment, and then went on to do a postdoc at the Kennedy School of Government at Harvard University. So we really look forward to your talk, Empowering Global Change with Life Cycle Assessment. And with that, I'll turn the floor over to you.
Thank you so much. All right, thank you so much. It's really great to be here. For those of you who are at my job talk, there will be a little bit of overlap, but I promise to present you with some new materials too. And great to see some folks that I haven't met as well. And thank you for joining online. I'm really excited to give this talk. So just a quick introduction to my research group. I formed the Energy Technology and Policy Assessment Group, or ETAPA, a few years back. We have three key research areas, the first being environmental life cycle assessment. We also do techno-economic analysis, which essentially does an assessment of the economics of emerging and existing technologies. And then we also have a technology policy focus. You might have noticed I come from a science background, but I have held appointments and joint appointments in policy schools as well. So from that, there's a bit of a focus on innovation and examining the role of innovation systems in advancing technologies towards full deployment in an energy systems perspective. So from this, we've had a number of publications coming out of my group focusing increasingly on taking a look at how to enhance and improve these specific methodologies to better account for spatial temporal context. And I'll explain a little bit more. Before I go on, I just wanted to say the present of the papers and ideas that I'm presenting, I have a lot of collaborators. So I just wanted to acknowledge them. And more recently, we'll be doing and have some proposed work with McGill as well that I'm really excited to get started. There's a bit of a US focus. I am Canadian, but I've been back and forth for about 10 years. So I'm really excited to be back and to starting this research here as well. So as a quick introduction, environmental life cycle assessment is a quantitative tool which is used to analyze the environmental burdens of products and processes from cradle to grave, or from materials extraction through waste disposal. So essentially, it's a technology assessment tool, so that can be applied for decision support by better informing sustainability and superior environmental outcomes. So here are a few diagrams which help show you. This right here is the method, the materials extraction, this cartoon here, materials processing, manufacture use through waste management. And above, you will see the method that's used, the one that's next to the box, which is shows the steps. The steps in life cycle assessment, and as well as in a life cycle assessment model, which you'll see here with the materials extraction, all the data inputs. So how can environmental life cycle assessment contribute to solutions? So within environmental life cycle assessment, there's a lot of carbon footprinting, for example. Carbon footprinting is in line with overall environmental life cycle assessment methodology. And it's now just this year, or a few years back now, the most recent IPCC that states it's unequivocal that humans have warmed the planet. Okay, so climate change is among the biggest challenges facing our society, and how to reduce emissions is something that we should all be part of. So life cycle assessment has typically been used to quantify sustainability impacts, and climate change being one of them. It's a resource and data-hungry analysis tool, so typically it was very limited in terms of how much you can integrate geographically and temporally resolved information. But in recent years, with all the new data science techniques and the proliferation of data, there's a lot of opportunity to really move and revolutionize this type of technique to ensure that we're considering the full impacts of our energy decisions. So the goal of a lot of my research has been to improve the spatial temporal resolution of systems level LCA, so not just looking at products, and to better inform technology policy decisions as we seek to transition our energy sources. So what I'll talk about today is I'll talk about some results from macro scale global decisions, and then I'll couple that with the need to better inform site level spatially resolved data intensive decisions. So just as a start, this is a systematic review that I published with my research group. And what essentially this did, we essentially we have a Python scraper that scraped the internet for published articles, which examined how spatial temporal information was resolved in electricity generation life cycle assessments. So what this essentially shows, if you look on the top, we had quite a few articles, over 6,000, which we then screened according to a number of criteria, and came down to about 251 from which we can derive information about the state of science in LCA as it relates to spatial temporal resolution. And so you'll see on this side here this large figure. So we're not going to go into all of these in detail, but what I do want to point out is that there's a lot of zeros, okay? So there's a lot of zeros as you start to get more spatial temporally resolved, as we're entering a time with a lot of greater data availability. Now you will notice, however, there are a few points where you can actually see that there have been LCAs conducted, for example, that are at the scale of a city or a site and hourly data or monthly data. So that to me indicates there's a huge opportunity to really improve this method by advancing spatial temporal techniques. And when we looked at these particular tools which had used more spatial temporal information, you'll see that we examined the analysis tools. So this is this other figure here which shows the trends. And we determined that geographic information systems and optimizations were the two greatest analysis tools that are used as we start to move towards having greater granularity in life cycle assessment. So what does this mean for my research? How did I get there? So I started off by looking at traditional life cycle assessments of gas-fired electricity. So as a very broad, simplified process, this diagram here shows gas production in the supply chain, so extraction, through processing. Then you have pipelines and midstream data, which can either go through ocean transport to the end use or through other transmission lines to the end use. And what we determined early on as we were starting to examine this system is that there actually isn't really a lot of spatial information involved in these analyses. So we compiled all the existing LCAs at that period of time, which contained data that we could examine. And we determined things, for example, like a lot of the underlying assumptions were the same, even though these extraction techniques may occur in different regions. So from this study, we then took the information and data, and we determined that the assumptions made about about where the extraction and the burning of the electricity, of the natural gas combustion occurs, can actually have a really big impact on the results. So what you see here is life cycle emissions in grams of CO2 per kilowatt hour delivered. And this is all the potential markets where liquefied natural gas can go, where natural gas can go over the ocean and be combusted for electricity. And if you take into account what the state of that electricity generation fleet, for example, you'll find that there's varying efficiencies. And in addition, the overall emissions intensity also depends on how well the transmission grid can actually deliver electrons to the consumer. So those electrons might be lost. And in those cases, you have to generate more to meet the consumer. So as a result, we found that these assumptions that you place on efficiency and transmission and distribution efficiency of power plants can really have a big impact on what your results are. And these were not well taken into account in the existing studies. So this led to questions about, well, what does this mean for how we examine the whole world of electricity generation? Okay, so I sat down with my colleague, Kavita Sarana, and we started discussing this question of transmission and distribution infrastructure. And what we found was that it's actually really not well represented in environmental life cycle assessment. So if you look at these particular photos, you might notice that there could be some distribution areas where there could be a lot of wires, for example, that aren't efficiently connecting to the consumer, or very long distances where potentially, for example, the amount of the quality of the metals, for example, isn't high, so there could be electricity that's lost in that transmission. So there's two key categories of inefficiencies that might occur. The first being technical losses. So that means that there's physical limits. Okay, so for example, you might have losses from resistance, aging infrastructure, for example. Maybe there's a need for additional maintenance and operation of the grid that isn't conducted. And then there are non-technical losses. Now, non-technical losses are a bit trickier because they can be related to things like pilferage, stealing, fraud, inefficient metering, and tampering. So because of those are definitely a little bit more challenging, but certainly can affect the overall operation of your grid. So the transmission and distribution losses, when I talk about it, I'm talking about the percentage of electricity generated that's lost between the source of supply and the distribution to the customer in those grid systems. And when I refer to compensatory generation, that's because power plants essentially are required to generate more than a kilowatt hour to deliver a kilowatt hour to the consumer. And that additional electricity generation results in emissions. So what my colleague and I sought out to do was to say, well, what are the emissions associated with these T&D losses globally? We figured out they mattered in that early publication. We've determined already that, okay, people aren't really taking into account spatial temporal resolution within LCA. So we determined to quantify these. Further, we took a look to say, okay, well, we know that presently, especially with the early NDCs, we're not on track to meet Paris goals. So our country is actually taking these emissions losses into account. Well, it turns out they weren't. At this time, for example, we did a review of the nationally determined contribution, so how countries will contribute to Paris goals, and only 32 at that time mentioned grid efficiency or T&D loss reduction, whereas 110 mentioned renewables. So this indicated to us that, well, maybe this is an opportunity by which we can actually figure out some ways to reduce emissions that people aren't thinking about. This is a large-scale systematic review that was conducted by the National Renewable Energy Laboratory. So what they did is they essentially compiled a whole bunch of information about existing emissions. So they essentially bounded all existing emissions estimates for greenhouse gas emissions according to different types of technology. So photovoltaics, hydropower, wind energy, all the way up to oil and gas. And this is in grams of CO2 equivalent per kilowatt hour. So this provides a rich data source by which we can characterize the uncertainty associated with electricity generation on the grid. So our question was, how do T&D losses matter? So that prior review represents the state of the art at that time. And what we determined was, when we looked through the information, that if we think through the life cycle, so fuel supply, delivery to the power plant, electricity generation, transmission and distribution, you see on this first figure right here, most of these are actually looking at the electricity generated and not delivered. So what we did is we took this simple shift in systems boundaries in order to actually include the transmission and distribution losses. So what exactly was that system, that simple shift look like? Well, let's start with how we went about examining each country. So we looked at over 142 countries, and for each of these countries, we characterized their grid mixes. Okay, so we characterized their grid mixes to take a look, and then we quantified what the emissions reductions could look like. Okay, so we took the emissions that we calculated in each country and made estimates for if they reached modern levels of transmission and distribution efficiencies, so aligned with your typical OECD average. And we determined that the emissions associated with these losses on the grid can result in upwards of as much as 1 billion tons of carbon dioxide equivalent every year. That's a lot of emissions, okay? So greater than the emissions of all of Canada, for example. And so what we determined was by making some simple changes to modernize the grid, you can reduce these by about half. Okay, so some very simple ways to get to potential emissions improvements simply by improving grids. So what we did with this, for each of the 142 countries that we examined, we quantified what the emissions look like. And just to give you an idea, so you might have emissions, for example, per each kilowatt hour, and you might be a very efficient country, but if you have a large amount of emissions, then the amount of emissions that are compensatory emissions can still be very high. So if you take a look at the top figure, for example, the reductions in emissions factor, so that's the grams of CO2 equivalent per kilowatt hour, you'll notice that, of course, for example, the United States tends to be quite low. Similarly with China. However, if you then look at the bottom figure here, which is the emissions reductions in megatons of CO2 equivalent per year, then those are much larger because they're much larger sources of electricity, or they generate a lot more electricity. So taking into account the importance of looking not just at the life cycle emissions, but also incorporating the overall implication for emissions globally. So how might this impact future emissions outcomes? Well, we took a look at this as well, and we said, okay, looking into the future, does this matter? So we looked at a number of different scenarios, the current policy scenario, new policy scenario, and the sustainable development scenario. So I'll just highlight the sustainable development scenario, which was the one that met the IPCC, okay? Current policies were those that were in place at the time. So this is a figure that we developed to show the emissions benefits of reducing transmission and distribution losses. So these are the potential improvements to the grid. So you'll see, for example, if you look at 2040, then we can seek to reduce almost 1 billion tons of carbon dioxide a year if there are no changes in the grid. But what is this little green one right here? Well, it looks like there's not very many emission savings, right? So it's like, okay, this is grams of CO2 equivalent, megatons of CO2 equivalent and emissions reductions, okay? So it looks like you don't really reduce very much, for example, in the sustainable development scenario. But just remember that this applies to all electricity generation sources. So what this does, it essentially enables more renewable electricity to meet grid demand, okay? So there's still a lot of benefits that are captured within that scenario as well. Okay, so potential solutions. So I just want to emphasize that we did a broad scale analysis, and this really points to the need to develop much more refined country level modeling tools to determine specific solutions. So specific solutions like improving transmission efficiency, so you might seek to replace inefficient wires, for example, controlling power flow, high voltage DC lines. You might also seek to improve distribution efficiency. So you might seek to have better load management, for example, increasing rated voltage. But there's also the potential solutions for reducing non-technical losses. Now remember, if you reduce non-technical losses, it won't necessarily be a one-to-one reduction in losses because there's stealing or pilferage in some countries. Because there's not necessarily the same level of access, for example. So if that's the case, so you might not necessarily reduce emissions, but you'll make the system more efficient. And those types of solutions might include tamper-proof meters, for example. And so I'll take another step back to talk a little bit more about gigaton scale solutions. This is another recently published article in Nature Climate Change. So if we start to think about global assessments of different electricity sources, in this case we're going to talk a little bit more about natural gas. I got concerned at some point about the amount of natural gas that's growing, and so I asked myself, as I looked through a lot of the global projections, how low can we necessarily go in terms of the emissions associated with this system? So what we see here is a figure which shows the life cycle assessment boundary associated with natural gas-fired electricity. So you'll see here there's natural gas. You might have domestic consumption. However, there may also be natural gas that comes in and is imported from elsewhere. Okay, so it's not always natural gas that's coming in from the same country anymore. So it's important to start to take that into account. You'll see you have the boundary here, which is the blue square, and then this is the reference country inside, where the natural gas might come from a variety of sources, especially as we're starting to expand global markets. But the power to actually reduce these emissions you'll see in this other figure, which we call jurisdictional. So that means that we have a different perception when we think about how we can actually address these emissions. So in this analysis, we looked at 108 countries that were generating natural gas-fired electricity in 2017. So we asked the questions about how do these life cycle emissions vary by country, and where are the emissions being released, and more importantly, how can we reduce them? So I won't go a step through the full model, but we did incorporate a lot of different information about the whole system, production of natural gas, gathering pipelines, storage, processing, transmission, and then different modes of transport to the destination country. And finally, the combustion for electricity generation. But with that, we have a whole bunch of different ways that we can reduce those emissions. Of course, you can switch fuels. But with a lot of the projections we were looking at, we were still seeing a large presence of natural gas in the system. So we said, okay, well, how can we necessarily reduce these emissions if it is going to be part of our system? So we then, for these 108 countries, quantified the life cycle emissions, greenhouse gas emissions, and determined that there was large variability across the countries, okay, which makes sense. But it ranged from just over 300 to near 1,400 grams of CO2 equivalent per kilowatt hour, okay? Coal is roughly around between 900 and 1,000. So it shows that it can span up higher, which is actually consistent with existing estimates. We determined that the electricity generation component contributes about 70% of the emissions, and that efficiency and combined heat and power can have a substantial impact on the results. Okay, so we found that, for example, Russia, if you exclude CHP, has a very high emissions intensity. This is using the IEA data of about 1,500 grams of CO2 per kilowatt hour, but they have a lot of combined heat and power. So that generates a lot of efficiency gains. And so with those efficiency gains, it actually came to about the average, global average, which is their result was about 615. And these were comparable, we found, to the International Energy Agency estimates, noting that our estimates included transmission and distribution losses, and so they are larger than the International Energy Agency, so that is what we determined is likely the factor. Okay, then we said, well, if you take into account an emissions factor, so grams of CO2 equivalent per unit electricity generated, we still have to think about jurisdiction. So overall, we found that globally there's about 3.6 gigatons of carbon dioxide equivalent that are emitted every year. For reference, that's about 10% of energy-related emissions, so it's big. And so a lot of it is from electricity generation, but how do we manage that, okay? So what we then did is we applied all these mitigation technologies to this system to determine what the potential impact was. So we, as mentioned before, we have reductions in fugitive methane emissions. We looked at reducing the upstream electricity transmission and distribution losses, pipeline transportation, power plant efficiency. We have carbon capture and storage. And we applied all of these at once to determine what the potential emissions reductions could be, and determined that they could be as high as 71%. So that means 2.5 gigatons of carbon dioxide equivalent each year could be reduced using these mitigation techniques. So we ran a sensitivity analysis. I'm not going to talk about this too much because we might run out of time. But what I'm going to, if you have questions about uncertainty and our assumptions, we can go back there as well. But I did want to spend a little bit of time to point out that if you look at these emissions cumulatively, they quickly get very large. So we linearly estimated over specific timeframes how many emissions can be reduced. So we have very large numbers of emissions, so 46 gigatons of CO2 equivalent per year, for example. By 2050, if you linearly extrapolate these, which is greater than the annual emissions every year. Okay, so very quickly, energy related, so very quickly it can actually become substantial. But I also wanted to spend a little bit of time to point out, well, some of these are cost effective. So there are ways that you can capture and reduce methane and sell it. And that can actually be cost effective. So that means that there's, for example, the International Energy Agency estimates 43% of these emissions from the methane can be abated at no cost because you can then sell the methane, okay? That's really great when that can happen, but that's actually not true all the time. For example, carbon capture and storage, so that's when you capture the emissions at the stack and put it underground, or you might use it for something. The estimates range from about $50 to $100 per ton of CO2. So that you can imagine that can be substantial, particularly for countries with competing economic priorities. So we certainly also recommend that there may be situations and conditions whereby other options may be the best and most effective mitigation alternative. Okay, so we're going to talk a little bit more about finer scale solutions. So this is great. We've talked about these huge macro scale solutions and emissions, but we can't really seek to solve these problems without thinking through what happens at sites and places and how we're necessarily going to go about changing the systems. So finer scales, essentially, we can argue are critical for implementation. Okay, first of all, this is a study which looked at the US, or actually this was the full Western interconnection. So the Western interconnection, I'll explain a little bit more, but what I will start by explaining is that if we look at optimization models, for example, where are we? Capture grid now. Okay, so we often, if we seek to look at how a grid operates, you might seek to develop, for example, an optimization model. An optimization model, you seek to develop a system where you minimize costs. Some of these models can account for environmental constraints, okay? So if you remember back to the beginning of the session, I talked about the coupled analysis tools. One of them was GIS, another one was optimization models. So we've already been using GIS. In this particular case, we're going to talk about a cost optimization model. So if you seek to cost optimize a grid, for example, using the model we looked at, we determined that these models which characterize hourly dispatch associated with grids under specific systems, conditions can underestimate life cycle emissions. So if you just look at grid emissions, you're actually missing about 18 to 30 roughly % of the emissions associated with the grid. So we wanted to examine this question a little bit more and say, okay, well, in addition to that, can we seek to develop some solutions? So we developed a life cycle approach to look at the greenhouse gas emissions of grid scale, renewable integration at the small scale, combined with examination of scenarios of carbon pricing. So if in the last slide we talked about how carbon capture and storage, for example, costs money, and renewables historically were more expensive. In this particular case, we're going to say, okay, as we start to integrate renewables, what are our options? So our study area was the full Western interconnection. So in the United States component was part or all of 14 states. We have Alberta, British Columbia, and a small slice of Mexico, which was approximately 265 gigawatts of generation capacity. Okay, so that'll make sense why I'm mentioning that in a minute. So we looked at this optimization model, which dispatched electricity to consumers in an optimized way, and sought to integrate these with life cycle assessment. So this particular model performed simultaneously co-optimized results for generation, transmission, and operations. This is coupled with my colleague Ben Hobbs's group, where we're looking into the future and examining the impacts of solutions on the grid. So similarly with our last model, we incorporated a large amount of different electricity generation technologies. And we also included different solutions such as pumped hydro, compressed air energy storage, battery energy storage systems, new transmission and wind capacity. Okay, so I'm just going to point out, and we also include different carbon pricing systems. Okay, so we looked at low carbon prices, so from $20 per ton CO2 up to $100. And so what we did, just as a little bit more granularity, we had examined a large number of different scenarios, about 21. And you'll see that we have about 1.2 gigawatts of pumped hydro. So if you look at these small system scale decisions, if you compare to 265 gigawatts for the full grid, it's actually relatively small. However, what it can do is point out the importance of implementing early stage solutions such as carbon pricing as we seek to transition. So these are the results for the scenarios and technologies. So what we looked at right here, if you look at this is the difference in the life cycle emissions across all technologies. So we have coal, petroleum, gas options, and then here are all the low carbon sources right here. So you'll see solar, PV, geothermal, and wind. And then this line, after that, we have all the different cost-optimized approaches implementing different carbon pricing systems and new technologies on the grid. So if you look a little bit closer, it looks like it doesn't really make much of a difference at all, right? But if we look a little bit closer and tease out how it matters, what we discovered was in situations where you're implementing small amounts of technologies that can help to reduce grid options, the impact of carbon pricing becomes more pronounced. Okay, so this is again greenhouse gas emissions per kilowatt hour. You'll see here's the base case, so that's you're running without having a carbon price or any scenarios. And then we have $20 a ton CO2, looking at different combinations of small incremental changes to the grid. So there's small changes across the technology configurations, but we see that carbon pricing can really have a big early impact on grid operations by discouraging large polluters to continue to emit. And then the more interesting thing that leads us to start thinking about how we can improve the system is that we can take these results and actually look at the impact on a temporal basis. So in this case, we have hourly emissions, hourly life cycle emissions under different carbon pricing schemes. Now this matters a lot because with these small changes, we see that the scenarios don't make a large difference, but we can think through what particular options might work best at what time. So it enables us to start to think through more powerful solutions for reducing emissions on the shorter term. And I'm going to spend a little bit of time, I'm just going to go through and talk a little bit about renewables because we don't have too much time left. And there's something I'd like to point out a little bit because I did promise that I would talk a little bit about, there is some data science in there, but just about some of the newer results that are coming out of my group that might be of interest. So this is from a 48-person workshop. So it's hard to read everything that's going on in this figure, but what I will tell you that we did is we had a 48-person workshop with the Electric Power Research Institute where we identified key critical areas where there's going to be environmental challenges associated with large-scale wind and solar deployment. So we're still going to run into challenges as we deploy lithium-ion batteries, solar, and wind. Now, that's not to mean we shouldn't be deploying them, but we should be thinking through solutions now. So we have these key themes right here. We have siting, public acceptance, wildlife issues, end-of-life issues, and then we seek to think through ways to improve the full life cycle. So you can see here, this is incorporating design, all of these issues from design all the way through decommissioning and thinking through how we can seek to reduce emissions across sustainable development goals. We spent a lot of time talking about carbon footprinting, so that's life cycle greenhouse gas emissions. Life cycle assessment does seek to span across environmental impact categories where possible, to ensure that you're not resulting in trade-offs to other impact categories. So there's a lot more that we can do in terms of actually expanding on these techniques. So we determined that of these environmental trade-offs, these really span all 17 sustainable development goals. So there's a lot of work that can be done to really start improving on them. I'm just going to focus on one. If you can't see this, one of the ones we talked about was confirming robust land use comparisons. So there's really lacking information in environmental life cycle assessment and more broadly about how energy actually impacts land. And then from that, there's been a large focus on the impact assessment component of within environmental life cycle assessment. But we don't even really have the inventories yet to even understand what the land footprint looks like. And it's often looked at as among the Achilles heels of solar and wind. And if you start to examine it more carefully, you'll see that there's things like techno-ecological synergies for solar. You can look at agrivoltaics, range voltaics, all kinds of different ways to reduce these impacts. And there's a real importance a real need to better understand how this might reduce the perceived impacts of deploying large-scale renewables. So one of the projects that my group has undertaken was a large-scale project looking at quantifying land impacts associated with energy systems in the U.S. Western Interconnection. But the idea is to go out broader. So there was a 2-year seed project that before this project started, just to understand the data that were out there that characterize the energy system. And so we completed that. We looked at hundreds of data sets that characterize energy that look all the way from fuel supply all the way to electricity generation. These are this is a little bit of information on the energy types that we looked at. We looked at natural gas, fuel supply through electricity generation, coal, uranium, so nuclear. And then we looked at several renewables, hydro, wind, and solar. Those specifically were without the fuel supply. Obviously, best case, we start to expand out on the long term and we can look at all the material inputs. But we're starting with this inventory. And ultimately, and then we compiled a large number of aerial images that are public. So it amounted to on the order of 12 terabytes that we analyzed. And so I'll give a quick example. So my postdoc did this amazing job of looking at these 12 terabytes of images to develop these inventories, which we hope are going to be really useful for life cycle assessment and all kinds of other modeling. And I said to him, it's really difficult to explain to people what exactly it looks like that you analyze, because it was amazing. We had this we worked with at Hopkins, the Institute for Data Intensive Science and Engineering. We had this big setup where we could actually look and examine very large data sets using specific software. So I said, by the time we get there, can we develop some GIFs or something? So he developed some GIFs. These are the GIFs. This is the area of study up here. You can look in, and these are all the wind farms. So it looks kind of like there could be quite a bit of data. He goes in and he buffers them in the area of interest. But when you start to think through what he actually completed, this is looking at the wind farms right here. This is one of the several hundred clusters that he looked at, where we went in and we essentially trained a deep learning model we teamed up with the computer vision lab. My group developed or analyzed thousands of images just for the training of this model. Now, granted, the challenge with geospatial and Earth observation is that the images aren't black and white. You don't have very many binary systems because the images are complex. Okay, so in this particular case, this is the first time we compared, this is the wind results, so we are comparing to the prior wind studies. So if you see this box plot here, the red box plots are prior studies that did this that had much smaller data sets associated with them. And so those particular studies made quite big assumptions about what the wind looked like. Some of them had small study areas and did very detailed analyses, whereas others examined and made large assumptions about what the land associated with wind looked like. Now, we went in and quantified and used this segmentation model to quantify over 16,000 individual wind turbine sites, which we then used to feed into an analysis of the land use efficiency, so watts per square meter associated with wind. And what we're actually finding is it's already known, so a lot of the time people say wind, solar take huge amounts of land. With wind particularly, it's less than 5% of the actual wind farm area that's impacted. So that means there's a lot of opportunity for multiple use of that land. And there often is agriculture, all kinds of other things. So we wanted to do a lot of these studies to emphasize that. Instead of making broad assumptions about the wind farm, well, let's actually determine the actual impact. So you'll see this is obviously in developed land areas. This is likely one of the areas that we examined in agricultural areas, where you can actually see the co-benefits and the dual use of land very clearly. So important to actually start to think through how we can develop inventories to demonstrate this and to better explain it to the public as we seek to advance our knowledge of energy systems and as we transition. Okay, so, and I'm going to get into, so obviously it's a little bit more complicated than that. I'll talk a little bit more about the site level in a minute. But I did want to emphasize the need for circularity, so I'll be starting some work here at McGill focused specifically on batteries, and also as we think through carbon capture and storage and CCUS, so you can actually use the carbon to develop specific products. So it could be concrete, all kinds of other things. So real need to use LCA to think through how to move towards a more sustainable system, examining these types of trade-offs. A lot of them still aren't cost effective yet. I just did want to point out, so one example, if you look at bioplastics, so I did one study that examined bioplastics and the costs and environmental trade-offs. That was with Andrew Redinger. His name isn't on here. It should be on here. And so we did LCA of this particular technology. Now what we found, it's not economical yet, and it's also really important to think through the fate of the CO2. So it's great that we have a biodegradable bioplastic, and we can, but what ultimately happens to the CO2 that's stored in it. So the fate matters, but also it matters what you're displacing, if you're displacing a more carbon-intensive process. Okay, so why did I call this whole presentation Empowering Change? So I'm going to give a quick call out to UC Davis because I gave this seminar there recently, and they said we want all of our speakers to talk a little bit about EDI or DEI in the US, so equity, diversity, and inclusion. But it's also really important in this particular case here. So you saw those images where we're looking at exact site level, and we can quantify the impacts, but it really matters what happens on the ground too. So public level acceptance. And there's a lot of importance about location and demographics. So also there's a lot of missing information and missing data. I don't know if you recall, but for example, for the global gas study, we did about 100 countries. The transmission and distribution, about 142 countries. So we didn't look at all global countries. So missing data also points to challenges about why we don't have that information. And certainly not all that information is perfect. So I just wanted to point this out, that thinking spatially, whether it's at the site level or global level, can really point out not only disproportionate impacts to vulnerable populations, but the need to really improve capacity and access to data and the development of data. And while LCA really does not do EDI well on its own, it's really, I just wanted to point out that these types of approaches really should be combined with more comprehensive decision frameworks that really reflect the need to incorporate environmental justice. And I think moving to more spatially temporal, like these very contextualized approaches where we can actually say something about space and time, is giving us a lot more opportunity to do that. Okay, so moving forward, I just want to leave some time for questions. Really, LCA, I hope this has shown to you how this type of approach can really help inform a more sustainable electric sector, and also to include equity in the ways that I mentioned, combined with other types of decision frameworks. One of the most rewarding things in my career so far has been determining some of these macro scale solutions. We have a very large challenge ahead of us in terms of the environmental impacts of our energy system. We're lucky to have an energy system where we can do a lot of things, but it comes with challenges. And if we can point out some of the ways that we can reduce these emissions, it's a very powerful thing to be able to do. But at the same time, it's important to refine analysis within countries, because we can say as much as we want about the macro scale, but it's really what happens from the ground up that's going to result in systematic change. So this can actually point out things such as carbon pricing, but I do want to end with the note that as we think through the energy system and how it's going to change, it's really critical. So we talked a lot about climate here, but it's really critical to move beyond that, because as we start to implement large-scale renewables with storage and batteries, or even CCUS and other, there's going to be a lot of additional opportunities for linking with reducing broader sustainability impacts, sustainable development goals, better aligning with the sustainable development goals, and recognizing costs and opportunities for impacts such as waste or land, like I mentioned, and thinking through circularity, not just with things such as batteries, solar, wind turbine blades, but also CO2 circularity. So what are we going to do? If we do capture the CO2, are there ways that we can put it back into our system that it's not going to be re-emitted into the environment, or that we can reduce the overall net emissions? Thank you so much for your attention. It's a little hard to hear you. Would you be able to speak up a little? Thank you.
So thank you for your presentation. I'm wondering if you could speak about what the private sector are doing with regards to scope 3 data. So we see a lot of startup in the climate tech space trying to sell all kinds of data solution, and they claim that they gather data and they have fine resolution of all these things. So is that something you've looked at, or is that something you have perspective on?
Well, so this is a very broad question, scope 3 and measurements. Do you mean actually measuring data from the source?
Well, what I'm saying is that the financial sector is putting pressure on companies to report more and more accurate scope 3 data. And so a lot of the companies, they do a spend-based method. So they just say we spend X dollar, and in that sector, that's Y tons. So that's very...
Oh, that's very good. Yeah.
More and more companies are trying to sell this granular information to improve the scope estimate.
Right.
I'm sort of trying to understand where that fits your work.
Yeah, no, this is really good. This is a really good question. So the question is about, okay, so we have more financial, and it's not just financial companies, it's governments and international governments even, that want companies to better report scope 3 or broader life cycle questions. And so it was previously looked at in terms of economics. So it would say, we know that a sector emits X amount, so we spend that much, so that's roughly how much the overall emissions are. But now we have a bunch of companies which are seeking to sell information and sell data. So and the question is, what do I think about that? What does it mean for this work?
I guess the question is, I don't know if you have thought about that.
So yeah, no, I have thought about it. So Yeah, no, and it really does depend on where you get it from. And there are some really good studies that are coming out. Obviously, the more resolved the information is, the better in terms of understanding how you can have really positive change. So for example, if you have a grid with high levels of renewables, if you understand better when there is ramping, ramping can actually create higher levels of emissions for combustion units. So having that level of information is good. Further, there's measurement sensors everywhere now. So we're actually getting to the point, I don't think that, that science has really comprehended at this point. Maybe there's a few areas where they have the sheer amount of emissions information that's going to be available. So two things. So my general perspective, I work in science, so I like to use open data as much as possible. Some of my analysis uses commercial data where I have agreements. Is, if you, to where possible, focus on, if you're interested in the public domain and information, it's always better to stick towards the public information. That's really expanding as well. Even the sheer amount of measurement data that we can have, for example, of natural gas production systems is huge. But it's really important to make sure that there's verification and that the data that's being employed is credible. So I haven't looked at all the data sources that you have, but that verification credibility component is obviously really big, really pointing to the need to better couple with ambient air measurements and additional existing measurements to ensure that they're well representative of what the system looks like. Now, mind you, I'll just point out one other thing. I don't think I've ever seen a perfect emissions data set. So even if you have very precise locations about a specific system, there's undoubtedly going to be some challenge associated. It may not cover every single system, or what time of day are the measurements occurring. So really important, first and foremost, to understand the data. And just a last point, the call for society to ensure that information is accurate is getting bigger than ever. So if you look at the EU methane strategy, for example, there's a really big push globally to ensure that there is credible information about the life cycle emissions of gas-fired power, especially now that we have the global methane pledge. Okay, so those upstream emissions, even if you're seeking to export to the EU in the middle of an energy crisis, there's an increasing need to verify that there is not a large amount of emissions being released across the supply chain. So it's going to become even more important. So that's a great question, is how do we ensure what's being reported is credible? And we should keep asking that.
There's another question in the back there. Go ahead.
Yes, I have a question. A little more specific, but earlier in the presentation you gave a show of the transmission and distribution losses for various countries, and there was a few of them, Syria, Iraq, and Togo, that I remember had extremely high, 60+%. How does one manage to lose 60% of your electricity? How does that work? And how did you find that, basically?
I think I actually have one example here. Yeah, so can you see this?
Yeah.
Yeah, so this is Iraq. And then you see what happened. So what happened around here?
Invasion of Iraq.
Right. And what happens during invasions?
Lots of infrastructure gets blown up.
That's right. Yeah, so it's often things like that, or it could be natural disasters like Haiti, or things, and then just the inability to recover. So some of it is quite astonishing. Now I'm really glad you pointed, I've been keeping this slide for this question, and I've presented this research, I think, a good dozen, I don't know how many times, so thanks so much for asking me. The other thing I'm going to point out too is that the International Energy Agency data that we use across all these countries is reported data, okay? So it's just important to keep that in context. And that's why we really emphasize that, it's really emphasized in a lot of my work that the need to really go in and really refine these to account for the spatial temporal context. So it gives you a macro scale view on an issue, but the real solutions would need to go in and actually do some very robust grid modeling. So that's the second part of the question. So I hope that answers.
Yeah. So let's say for Haiti, where there's 60% transmission and distribution losses, is that saying that of your 100% generated electricity from power plants in Haiti, 60% is lost before it reaches the consumer?
So that would be, that's what is reported by the International Energy Agency as lost, but I would also caution a little bit because often in systems where you have an emergency response, there's often small generators. Now the counter side to that is they're often diesel. So they're not often very clean generators, so it wouldn't necessarily represent all energy that would be consumed. And these are not static numbers either, okay?
Okay, cool. Thank you.
Thanks for the question.
We'll take one last question, Professor Navarro.
Yeah, thanks. Great talk. One thing that I observed just as it was coming through this the discussion is that a lot of this approach motivates excellence across different industries. It's sort of a top-down initiatives for better monitoring is part of what can enable improvement of infrastructure, for example, in local countries, for example, to prevent losses of methane, and especially looking at what it could mean to have better control for temporal data. And do you see possibilities to interact with specific industries for increasing their operational excellence, let's say the top-down monitoring initiatives to enable bottom-up initiatives for operational excellence?
Yeah, this is a really great point, actually. And I think, you know, so LCA, as you know, is designed to produce solutions, whether it's modifications in the design or changes in operations that result in lower emissions or better sustainability performance. And one way that you can do that is by showing, for example, using a broad average and then showing how much better it can, that those results can be if you employ specific techniques. So I think that's a very powerful and useful way to explain the benefits of operational excellence.
Thank you. Well, before we conclude formally, I would like to take the opportunity to thank the Trottier Family Foundation and our other benefactors who made events such as this and all of the work at TISED possible. So with that, have a great afternoon and thank you so much for a wonderful talk.
Thank you.